Welcome everyone. I'm happy to be here with you, at least virtually for this new SIPTA seminars. I'm also very happy that today we will have Thierry Denoeux speaking about a very recent advance on belief functions and learning. So you have all the information on the slides normally, as well as the next seminar. So that's it for the general introduction. And without further ado, I will hand over the microphone to Benjamin Coste, who will animate this seminar. So thank you, Benjamin, for doing this. Thank you, Thierry, for accepting to give this seminar. And Benjamin, you have the floor.
Thank you, Sam. So good afternoon. It's a pleasure to welcome you to this 9th SIPTA online seminar. And as Sébastien said, we have a pleasure today to welcome Thierry Denoeux. So a few words about Thierry. He's a full professor with the Department of Computer Science at the Université de Technologie de Compiègne in France. He's also a senior member of Institut Universitaire de France, so the French Academic Institute. And very broadly, his research addresses dealing with uncertainty in intelligent systems, machine learning, data science, and so on. So Thierry is mainly known for his works in the theory of belief functions, for which he has made a number of significant contributions, very significant contributions. And these contributions are not only upstream, but also encompass notable applications to machine learning, to pattern recognition, statistical inference, information fusion. And Thierry has published a lot of papers on these topics. I don't have the exact count in mind, but over 300, something like that. Thierry is also known in the community, interested in reasoning under uncertainty, since he's the editor-in-chief of iJar. He's also involved in other journals related to dealing with uncertainty, such as fuzzy sets and system. And today he's going to give a talk on random fuzzy sets and belief functions with an application to machine learning. Okay, so I'll leave now the floor to Thierry and enjoy.
Okay, good afternoon, everyone. Thank you, Benjamin, for this introduction. Thank you, Sébastien, Jasper, and Enrique for inviting me in the seminar and also for organizing this seminar, which I think is it's a great idea to have a seminar and very useful for the community. Okay, today I would like to talk about my recent research work on the theory of epistemic random fuzzy sets, which I see as an extension of the Dempster-Shafer theory of belief functions. And I will try to show you some application of these ideas to machine learning. Okay, as we all know, monolithic uncertainty is a fundamental problem in AI. Related issues are representing uncertain, imperfect knowledge, reasoning, and decision-making with uncertainty, and the quantification of prediction uncertainty in machine learning, which has been a hot topic in recent years. So there exist quite a lot of models, leaving aside the Bayesian probability theory, which is still now the, let's say, mainstream approach. Two of the most widely used models are Dempster-Shafer theory and possibility theory. Dempster-Shafer theory is based on two main ideas. First, representing evidence by belief functions, and then a particular operator for combining independent pieces of evidence, which is called Dempster's rule. It is based on random sets, and it generalizes Bayesian probability theory. In contrast, possibility theory uses possibility distributions for representing uncertain information and triangular norms for combining information from different sources. So in this talk, I would like to try to justify the following claims. First, these two theories, mainly Dempster-Shafer theory and possibility theory, are distinct. It is sometimes claimed that possibility theory is a special case of Dempster-Shafer theory because the possibility measure is a plausibility function in the sense of Dempster-Shafer theory. However, the mechanisms for updating information are different in the two theories. Second claim is that these two approaches need to be used simultaneously in some applications. Okay. And so the conclusion I try to argue for is that we need to embed them into a more general framework. Okay, as an illustration of an application where we need both approaches, I will mention statistical inference. In his 1976 book, Shafer proposed to interpret the relative likelihood as defining a consonant belief function, which, as we know, is mathematically equivalent to a possibility distribution. And a nice feature of this approach to inference is that combining the likelihood-based belief function with a Bayesian prior by Dempster's rule yields a Bayesian posterior. So this approach can be seen as a kind of a prior-free Bayesian inference. However, the relative likelihood functions from independent samples cannot be combined by Dempster's rule because the result would not be consonant anymore. So they must be combined by the normalized product T-norm, which makes sense in possibility theory. So Shafer of course, was aware of this kind of contradiction, and he later abandoned this approach. I personally think that this approach is quite interesting. And to make it consistent, I propose to place it in more general mathematical framework that encompasses both possibility and Dempster-Shafer theories. Okay, so I will not elaborate much more on this in this talk because I will cover other topics, but if some of you are interested, I refer you to some of my recent papers. So in this talk, there will be three main parts. I will first introduce what I think is a new model of uncertainty based on random fuzzy sets and a new combination rule for random fuzzy sets that generalizes both Dempster's rule and the normalized product intersection of possibility theory. Then I will define practical and easily combinable random fuzzy sets models that will allow us to, in particular, to represent uncertainty on continuous variables, something that was a little bit missing in the theory of belief functions. So the frame can be the real line or an interval or R to the P or the probability simplex and so on. And then I will demonstrate these ideas to the application of these ideas to machine learning. And in particular, I will describe a neural network model for regression that quantifies prediction uncertainty by random fuzzy sets, or more or less equivalently belief functions. So first, random fuzzy sets. So we assume that we start with two spaces, a probability space and a measurable space. And a random fuzzy set is a mapping x tilde from omega, the part of the probability space, to the set of fuzzy sets of another space, theta. And so this mapping needs to verify some measurability conditions. So it is required that for any alpha in 0, 1, the mapping denoted like this, x tilde alpha, which is a mapping from omega to the power set of theta, must be a random set. That is to say, it must be strongly measurable with respect to the two sigma algebras. Okay, so in what I call epistemic random fuzzy set theory, we use random fuzzy sets as a model of unreliable and fuzzy evidence. So in this approach, theta is a domain of an uncertain variable or quantity, theta, small theta. Omega is a set of interpretations of a piece of evidence about small theta. And the meaning is that if interpretation omega, small omega holds, we know that theta is constrained by the possibility distribution defined by the fuzzy set x tilde of omega. So this is a toy example to try to clarify this. Assume that a witness tells us that John is tall, and this witness is 50% reliable. Then we have two ways to interpret this formation. Either the witness is reliable or not. So there's a probability of 50% being reliable. Theta, let's say, is John's height in meters with that frame, that domain. And the image of reliable is tall, that can be defined formally as a fuzzy subset of big theta. And the image of not reliable is the whole set theta, because if the witness is not reliable, we don't know anything. So, of course, random fuzzy sets is not a new concept. It has been proposed already a long time ago. But our interpretation is different from previous interpretations of random fuzzy sets. either as a model of a random mechanism for generating fuzzy data, or even as a model of imperfect knowledge about a random variable. So here in the framework I just described, there is no random variable actually. So a random fuzzy set defines belief and plausibility function. So specifically, so assume that interpretation small omega holds, we can define the degrees of possibility and the degree of necessity that theta belongs to any measurable subset B of theta in the following way. So these are the classical operations or the definitions of possibility theory. So now we can define the expected possibility degree and the expected necessity degree that theta belongs to B. And so this idea was already proposed in a 1979 paper by Zadeh, which I think has been a little bit overlooked. And it can be shown that the expected necessity is a belief function, and the expected possibility is a dual plausibility function. So a random fuzzy set is, like a random set, a way of specifying a belief function, but the random fuzzy set model is more flexible, and we'll see that we can exploit this flexibility to define interesting practical models. So if a random fuzzy set defines a piece of evidence, we need a mechanism for combining evidence. So we now assume that we have two random fuzzy sets, okay, from two with sets of interpretation omega 1, omega 2. And we assume that they represent independent pieces of evidence. So if interpretations omega 1 and omega 2 both hold, we can deduce that theta is constrained by the image x tilde of omega 1 and by the image x tilde of 2 of omega 2. So it is constrained by the intersection, according to some definition of fuzzy intersection. Okay. So to make things more specific, we need first a definition of fuzzy intersection, and second, a way to handle possible conflict or inconsistency between the two sources. So for fuzzy intersection, it is known in probability theory that the product T norm is the most suitable for combining information from independent sources. And so I will use the normalized product intersection, which is defined in that way. We just multiply the membership function, so the two fuzzy sets here, F tilde and G tilde, and we normalize the product by dividing by the height of the product. The advantage of this operation is that it is associative, whereas if you choose other T norms, generally the normalized combination is not associative. Then there is conflict. And we know that in Dempster's rule, there is some normalization operation that takes place to eliminate conflicting or to condition on the pairs of conflicting, non-conflicting interpretations. So with fuzzy sets, conflict is a matter of degree. So we can define the fuzzy set of consistent pairs of interpretation like this. So this is a fuzzy subset of omega 1, big omega 1 cross big omega 2. And so the degree of consistency here is measured by the height of the product, okay, of the images of omega 1 and omega 2 by the two mappings. And so the probability measure on the product space will be obtained by conditioning the product measure by this fuzzy event, okay, where we use here a definition of the probability of a fuzzy event also proposed by Zadeh. Okay. And this process is called soft normalization. So now we can define a combined random fuzzy set that maps each pair omega 1, omega 2 to the normalized product intersection of the images of omega 1 and omega 2 by the two mappings. And this is associated with a product measure conditioned on the fuzzy subset of consistent interpretations. And so we get an operation on the random fuzzy sets, which I call the product intersection. And this is denoted like this. So some properties of this operation is that it is commutative, associative. It generalizes both Dempster's rule when applied to random sets and the normalized product intersection of possibility distributions. And it verifies this property, which is well known for belief functions. It is that the plausibility of singletons for the combined random fuzzy set is proportional to the product of the plausibilities by each of the belief functions. Okay, so we get now this general picture where we have these two theories of uncertainty: possibility theory based on fuzzy sets, Dempster-Shafer theory based on random sets, and on top of this, we have epistemic random fuzzy set theory based on random fuzzy sets. So here I have put in this picture a theory of lower previsions, okay, which I think it's important to mention it because I think a lot of people maybe in this community have an interest in this approach. To me, it doesn't fit in that main picture. It's to me a completely different approach, which also generalizes probability theory, but in a different way than does Dempster-Shafer theory. Okay, so here the broken lines here mean some mathematical connections between the frameworks. For instance, a possibility measure is a special plausibility function, and the belief function is a special lower prevision. But yet, at least in my view, and maybe we can have a discussion after my talk, these approaches are different because the ways to update or combine information are different in these three theories. Okay, now to make this approach operational in applications, we need practical models, okay, that are easy to define and to work with. And actually, in probability theory and statistics, the Gaussian probability distribution plays this role of a simple model that allows for easy calculation, manipulation, and so on. And until now, a similar workable model had been missing in Dempster-Shafer theory to represent uncertainty on continuous variables. Possibility distributions, or for instance, P boxes, are not so easy to use in the Dempster-Shafer framework because they are not closed under Dempster's rule. So here I will propose a model which I call Gaussian random fuzzy numbers, which is an extension of a Gaussian random variable. And and I will show that based on this simple model, we can define several families of belief functions on different continuous frames. And these families are closed under the product intersection operator so that they can fit nicely in this approach. So let me start with Gaussian random fuzzy numbers. And first, Gaussian fuzzy numbers. A Gaussian fuzzy number is a normal fuzzy subset of the real line whose membership function is Gaussian, like this. So we have here three examples. So it has two parameters, a mode and the precision parameter. And the interest of this model is that it is closed under the normalized product intersection. So the normalized product intersection of two Gaussian fuzzy numbers is still a Gaussian fuzzy number. So now I propose to define a Gaussian random fuzzy number as a Gaussian fuzzy number whose mode is a Gaussian random variable. So we can say that this model is like doubly Gaussian. So the membership function is Gaussian and the mode is random, or actually is probabilistic if you want. There's no actual notion of randomness here. The mode is a Gaussian random variable. And so it can be seen either as an uncertain Gaussian fuzzy number or as a fuzzy Gaussian random variable. Okay. So more formally, a Gaussian random fuzzy number with mean mu, variance sigma squared, and precision h is a random fuzzy set defined like this. So it's actually the image of each omega is a Gaussian fuzzy number, and the mode is a Gaussian random variable. Okay. So mu is a location parameter, sigma squared is a measure of an index of, let's say, variability, and H is defines the precision. And this is we write this in this way. So this is really an extension of Gaussian random variables with an additional parameter corresponding to, let's say, imprecision. So if the precision is 0, then the image of any omega is a real line, okay? And this corresponds to in this case, what we get is a vacuous belief function that corresponds to complete ignorance. If precision is infinite, then a Gaussian random fuzzy number is actually equivalent to a Gaussian random variable. And if the variance is 0, then we have something which is equivalent to a Gaussian possibility distribution. So the same model contains, as special cases, Gaussian random variables and Gaussian possibility distributions. So we can more or less easily do simple calculations with this model. For example, we can compute the plausibility of a singleton, which is called the contour function. And you can verify that when H becomes infinite, then this is equal to 0. Okay, so for a Gaussian random variable, the plausibility of any single real value is 0. We can compute the belief and the plausibility of an interval, xy, and you can verify then that we recover the usual formulas for Gaussian random variables when H, the precision, is infinite. And importantly, the family of Gaussian random fuzzy numbers is closed under the product intersection rule, which I described before. And you have this formula that allows you to compute the mean, variance, and precision of the combined Gaussian random, the result of the combination of two Gaussian random fuzzy variables. And we can also apply the same ideas to fuzzy vectors, random fuzzy vectors. So we can define a p-dimensional Gaussian fuzzy vector. Sorry. So first, as with mode M and a precision matrix H by this Gaussian, multidimensional Gaussian membership function. And then when the mode becomes a Gaussian random vector, then we get a notion of Gaussian random fuzzy vector. And once again, this family of random fuzzy sets is closed by product intersection. Okay, now this basic Gaussian model can be extended to accommodate different supports or even different shapes. And so some limitations of the Gaussian random fuzzy model are first that the domain is a whole real line. And so this model is not suitable for representing belief functions on, for example, a real interval. And on the other hand, the Gaussian random fuzzy number is unimodal and symmetric about the mean. And so it may not adequately reflect an agent's actual beliefs if there is some lack of symmetry, some skewness, and so on. So we need more flexible parametrized families of random fuzzy numbers and vectors with different supports and different shapes. And we still want to maintain the closure property with respect to the product intersection rule. And this can be achieved in at least two ways, complementary ways. Either we can compose a random fuzzy set with a one-to-one mapping from theta to another space. And so we get a new random fuzzy set. I should denote it by y tilde here, not x tilde. So this is the first idea. And second idea is to define mixtures of random fuzzy sets. So I will very briefly give an idea about these two, give some basic facts about these two ideas. So here we have a random fuzzy set x tilde from omega to theta. And we consider a one-to-one mapping psi from theta to some set lambda. Okay. And so we can first extend psi to fuzzy subsets of theta using Zade's extension principle. So we get mapping psi tilde from the set of fuzzy subsets of theta to the fuzzy subsets of lambda. And then the idea is to compose this mapping psi tilde with x tilde. And so we get a new mapping which can be proved to be a random fuzzy set. Okay. So we have these properties. So the belief and plausibility functions with respect to the composed mapping can easily be computed from the original belief and plausibility functions corresponding to x tilde on the one hand. And on the second hand, we have this very interesting property that you can first, if you have two random fuzzy sets x1 tilde and x2 tilde, you can first combine them and then compose this with psi tilde, or you can combine the composed mappings. So result is the same. So if this means that if x1 tilde and x2 tilde belong to a family of random fuzzy sets, which is closed under the product intersection, this is also true for the composed mappings. And I will show two examples. Assume that x tilde is a Gaussian random fuzzy number, and psi is the exponential function for the real line to the positive real line. Then the composed mapping is called a log normal random fuzzy number. It is a new random fuzzy number with support equal to the positive real line. And we write it like this. And we can easily define and combine such log normal random fuzzy numbers. So here to display a random fuzzy number, I show the blue lines are the lower and upper distribution functions, and that give the belief and the plausibility of the interval minus infinity, say y. In red, I show the plausibility contour function, and the dotted lines are some realization of the random fuzzy set. So I show here two examples of log normal random fuzzy numbers, one y1 tilde, y2 tilde, and their product intersection. We can also do something similar for starting from a random fuzzy vector. So for example, if x tilde is a Gaussian random fuzzy vector, and psi is a softmax transformation from R, let's say, to the p-1 to the p-dimensional simplex as p, then we get, by composing this extended softmax transformation with x tilde, we get a random fuzzy vector on with support equal to the probability simplex. I call it a logistic normal random fuzzy vector. And so, for instance, here I show some examples of fuzzy focal sets of a logistic normal random fuzzy vector in the three-dimensional probability simplex. So these are three. So on each graph here, you see the contours of the membership function of a fuzzy focal set. Okay. And the last plot here with the red lines correspond to the plausibility contour function. So this allows us to represent beliefs, for example, or evidence about, say, a probability. And this model becomes a logistic normal random variable if the precision becomes infinite. Okay. And we can also, and here I will mention this only very briefly without going into the details, but we can also define mixtures of Gaussian random fuzzy numbers or of transformed Gaussian random fuzzy numbers. So a mixture of Gaussian random fuzzy numbers is a Gaussian fuzzy number, Gaussian random fuzzy number, sorry, whose mode is a mixture of Gaussian random variables. And this can be also composed with a one-to-one mapping. And for instance, here I show two examples of logic normal random mixtures of Gaussian random fuzzy variables. numbers and their product intersection. Okay, so this is just an example to show that we can define, let's say, random fuzzy numbers of virtually any shape or complexity. And these random fuzzy numbers can be combined by our product intersection operator. Okay, now I will show you some application of this model to machine learning and more specifically to regression. Okay, so most of my work, big part of my work until now has been in what I've called evidential machine learning. Evidential machine learning is an approach to machine learning in which uncertainty is quantified by belief functions. And until now, most of the work has addressed either clustering or classification. And the main reason is that these learning tasks require only belief functions on finite frames. And most of the work on the Dempster-Shafer theory has been with finite frames because of this lack of, say, easily workable and practical models for defining belief functions on continuous frames. So now that we have this, the models I've just described, and we have simple ways of defining and combining belief functions on continuous frames, we can tackle other learning tasks, such as regression. So here I will consider a regression problem in which the task is to predict a continuous random response, variable y, from p predictors, x1 to xp, based on some learning set. And I will describe a neural network model, which I call ENN-reg, which computes for each input a Gaussian random fuzzy number with an associated belief function that represents uncertainty about y. And so in this model, uncertainty about the response is described by a Gaussian random fuzzy number. So this model is based on prototypes, and it is in some way a little bit similar to previous work I did on what I call the evidential neural network for classification, in which I defined prototypes, and the proximity or the distance to each prototype is used to define the belief function, and the belief function are combined by Dempster's rule. So here we have a similar idea, but here each prototype will, the evidence of each, say, of the distance to each prototype will be represented by a Gaussian random fuzzy number. Okay, so first the model. So we assume that we have k prototypes. A prototype is a vector in the p-dimensional input space. So we define the similarity between the input x and some prototype wk using a Gaussian kernel like this, where here gamma k is a positive scale parameter. And then we represent the evidence from prototype omega wk by a Gaussian random fuzzy number, this form, where here the mean is defined as a linear function of x. Okay, so we can say that locally in the neighborhood of prototype wk, we approximate the regression function by a linear function. Then the second parameter is the variance, parameter sigma k squared, which is can be seen as an estimate of the conditional variance of the response in the neighborhood of the prototype wk. And the precision is the product of a parameter hk multiplied by the degree of similarity. Okay, so it means that the farther the input to the prototype wk, the more imprecise, the weaker the evidence, and so the more imprecise the random fuzzy number. So the parameters in this model are the scale parameters, the variance, the precision, and the coefficients of the local linear equation. Then the output of the network is for input X is computed by combining the Gaussian random fuzzy numbers from each corresponding to each prototypes. So here I combine them with a variant of the rule I proposed before. It is a product intersection without the normalization step. And this is obviously to simplify the calculations. It can be seen as a kind of approximation when the conflict is not too large. And so we can easily compute the combined Gaussian random fuzzy number by these equations. So we can see these calculations as being performed in a neural network with that architecture. So it has two hidden layers. So you have the input layer and two hidden layers of 2 times k units. K is the number of prototypes. So in the first hidden layer, we have actually k pairs of units. One is a radial basis function unit that computes a similarity between x and prototype wk, and the other is a linear unit, okay, that computes the local linear mean. Okay, then in the next hidden layer, we have again k pairs of units. One computes the square of the similarity sk, and the other multiplies. It's a product unit that multiplies the similarity with the with mu k. And then we have the output layer with direct connection from the last hidden layer on the one hand, and cross-cut connections to the first hidden layer. Okay, so now the next step is learning and how to learn the parameters of this network. So obviously we need a loss function. So in the case of a probabilistic forecast, let's say with where we forecast y with a PDF, let's say f hat, we typically measure the prediction error or the loss by the negative log likelihood, which actually can be interpreted in the following way. Actually, we never observe a real number y with infinite precision, but an interval, say, of the form y minus epsilon, y plus epsilon. So an interval centered at y with a length 2 times epsilon. Epsilon can be seen as an infinitesimal value. And actually the probability of that interval is proportional to the density f hat of y. So that this negative log likelihood is actually the negative logarithm of the probability of that interval centered at y plus some constant. Okay, so now the question is, how can we generalize this to the case where prediction is given in the form of a belief function? So the first ideas that come to mind are to replace the probability either by the belief function or by the plausibility function. Actually, neither of these two solutions work, because if you take the belief function, the loss is always minimized by a Bayesian belief function. It means that this loss function does not reward imprecision at all. And if we take the plausibility, it also doesn't work because it is minimized by the vacuous belief function. Okay? Because we know that for the vacuous belief function, this plausibility is always, the plausibility of any event is always 1. So my proposal is to consider a weighted sum of these two terms. Here, lambda is a hyperparameter in 0, 1. Epsilon is also a hyperparameter to be defined. And actually, with this approach, smaller values of lambda correspond to more cautious predictions. So this is shown here by this graph, where I show the loss. So I assume that the truth is 0, and the prediction is a Gaussian random fuzzy number with mean 1, variance 1, and different values of h, the precision h. So, and we have different curves for different values of lambda. So lambda equals 0 is a blue curve here, and the minimum is for h equals 0. So this is for the vacuous belief function. if you take the red curve, this corresponds to lambda equal to 1. So you take into account the belief, and the minimum is obtained for h equally infinite. And for intermediate values of lambda, you have the minimum for some values of h. And so the larger lambda, the smaller h. We can also see that when the error is larger, here on the right-hand side, we see the loss when the prediction has a mean 5, so the error is larger, and we can see that the minimum loss is obtained for smaller values of h, which means that when the error is larger, the precision, the optimal precision is smaller. So for training the network I presented before, I propose to minimize the regularized average loss, where here there are two regularization terms. The first one actually is the effect of reducing the number of prototypes used for the prediction, because if you set hk to 0, this amounts to discarding prototype k. And the second regularizer has the effect of shrinking the solution towards a linear model, because setting gamma k to 0 for all k actually yields a linear model. So on the one hand, we want a solution which is say parsimonious in terms of prototypes, and on the other hand, we shrink the model towards a linear model. So we actually have 4 hyperparameters here, which maybe is a bit too much. So what I propose is to fix the first 2 heuristically, and then the other 2, which the psi and rho, are tuned by either the holdout method or cross-validation. Okay, another issue is calibration. So in the case of probabilistic forecast, we try to have calibrated prediction intervals. What can be a notion of calibration when the prediction is given in the form of a belief function? So the approach I've proposed is the following. So for any value alpha in 0, 1, we define an alpha level belief prediction interval as an interval centered on mu of x, on the mean, with a degree of belief equal to alpha. So a belief prediction, an alpha level belief prediction interval is an interval centered on the mode or the mean, and with a degree of belief equal to alpha. And I would say that the predictions are calibrated if for all alpha, the alpha levels belief prediction intervals have a coverage probability at least equal to alpha. Okay, so we expect the predictions to be conservative. Okay, of course, we also want these probabilities, the coverage probabilities, to be as close as possible to alpha, but we want them to be larger than or equal to alpha. And as in the probabilistic case, the calibration of evidential predictions can be checked graphically using a calibration plot. I will see some examples soon. And okay, something that can be done is, okay, actually we want the predictions to be conservative, but not too conservative. Okay, so what we can do is to, let's say, somehow calibrate the predictions after training by multiplying the precision output by some constant c, and so as to ensure this equation, these inequalities with predictions that are as precise as possible. So once again, I will show some applications later. So this is an example, okay, of simulated data with a nonlinear regression function and an error that has a variance that depends on x, that actually increases with x. And so here, what we can see on this graph, the blue broken line is a true regression function. The red solid line is the expected value, mu of x, and the intervals are belief prediction intervals at levels 50%, 90%, and 99%. Okay, so here we used a network with 30 prototypes, and the hyperparameter psi and rho were determined by minimizing validation mean squared error. And here we can see the calibration. So we have two curves. The blue curve shows the coverage rates for the probabilistic prediction intervals, okay, that you get by not taking into account the precision. Okay, you treat the output as you just consider the mu of x and sigma squared of x, and so it means that you assume the output is a Gaussian, a random variable, and you can see actually in that case the probabilistic prediction intervals are already calibrated in our sense, because that blue curve is above the diagonal. So this is a little conservative. And the red squares are the belief prediction intervals, which are a little bit more conservative, but not much more. Okay, so it means that for that case, the precision is quite high for the outputs. Okay, now some experimental results. So I have tested this method on the 10 widely used data sets, data used in the machine learning literature for evaluating regression methods. And this is a comparison with respect to the root mean squared error. So for the ENN-reg model, our model, and here we have radial basis functions, relevance vector machines, support vector machines, Gaussian process regression, random forest, and multilayer perceptrons. And what we can see, so here I show the standard errors. So, we can see that actually ENN-reg performs actually favorably, equally well, or sometimes better than the classical methods in terms of root mean squared error, or precision or prediction accuracy. So here I've done also the comparison with, say, more recent methods from state of the art. Here we have on the subset of the data sets I showed before, we have a comparison with probabilistic backpropagation, Monte Carlo dropout, deep ensembles, and deep evidential regression in terms of root mean squared errors and negative log likelihood. Negative log likelihood is often used as a measure of calibration. And so here I only consider the mu and sigma squared part of the predictions. And so even in terms of, say, probabilistic calibration, we can see that ENN-reg is quite competitive in terms of calibration with respect to what is considered the state of the art, like Monte Carlo dropout or deep evidential regression. And also in terms of prediction accuracy, we get ENN-reg is always either the best result or among the best, reaches the best results. So here we see some examples of calibration plots. So here we have on each graph we have three curves. So in blue, we have the probabilistic predictions. So considering only the mu and sigma squared outputs. So we treat the output as probabilistic outputs. The green curves with the triangles are the red squares they correspond to the evidential predictions, raw evidential predictions, and the green triangles are the adjusted evidential predictions. Okay, so what we achieve by, say, fine-tuning the calibration by multiplying the precision output by a constant C. And so here in that case, we see that, okay, depending on the value of alpha, the probabilistic interval is sometimes a little bit too confident, sometimes sometimes conservative. The evidential predictions are really conservative, and we can make a little bit more precise by this adjustment mechanism. So here, this is an example of another data set where the probabilistic predictions are really too confident. The raw evidential predictions are conservative, and again, we can make them a little bit more precise while still being conservative. And here we have two more examples. So here the this is an example where the raw evidential predictions are too confident. Okay, so here we need to multiply the precision outputs h of x by some constants smaller than 1 to make the outputs less precise. And so in that way, we can obtain conservative predictions. And here, this is the last example is a case where the probabilistic outputs are already conservative, okay? And the evidential outputs are even more conservative. So we can, in that case, we can multiply the precision by infinite, so that we can actually get we can use the probabilistic output in that case because they are already conservative. So to summarize, okay, so I have presented a theory of epistemic random fuzzy sets. I call them epistemic because this is an interpretation of random fuzzy sets that as representing evidence, okay, and beliefs. So this theory extends both possibility theory with the product intersection and Dempster-Shafer theory, and it allows us to represent and reason with uncertain, imprecise, and vague information. I have also defined several families of random fuzzy numbers and random fuzzy vectors indexed by 3 parameters, a location parameter, a variance parameter, and a precision parameter. And these models make it possible to define belief functions on continuous frames that can be easily manipulated and combined. And I think this actually overcomes the limitation of Dempster-Shafer theory. I think this opens the way to applying Dempster-Shafer theory to problems in which we have continuous variables without discretizing the variables. And then I've shown the evidential neural model of a regression neural network based on the Gaussian random fuzzy numbers. And the network output for an input x consists of 3 numbers: a point prediction, a variance that measures, say, random or arbitrary uncertainty, and a precision output that can be seen as representing epistemic uncertainty. And actually, experimental results show that this model performs as well as or better than state-of-the-art regression methods while providing conservative or cautious predictions. Okay, so these are some references to some of my recent papers. So the first one, in the first one, I introduced that epistemic random fuzzy set notion in the discrete finite case on finite frames. Then the second paper extends the model to continuous frames and introduces that Gaussian random fuzzy number model. And then the third one here is introduces the composition, the idea of composing a random fuzzy set with a one-to-one mapping to define a new random fuzzy set for example, with a bounded support, for instance, and also the idea of mixtures of random fuzzy sets. And this is a paper on the ENN reg model. And there is also an R package available with that ENN reg model. Okay, so that's it. Thank you for your attention, and I can take as many questions as needed.